So what we're going to talk about now is our improper integrals. So we have gone over so many integration techniques. We've learned, you started off with how did you do a definite integral. So remember, a definite integral means you were computing the area under a curve between A and B. That's what we mean by it's definite. And we started off with, doing things like the limit of a Riemann sum. That's what we defined it to be. And then we learned about the fundamental theorem of calculus. And then, you learned about things like U substitution, division by parts, trigonometric substitution, trigonometric integrals. Those are all ways that you could find an antiderivative to use the fundamental theorem of calculus. And then eventually we talked about how, sometimes you can't find an antiderivative. So what do you need to do? You basically need to use a numerical method, and that's what we covered last class, right? Last class was numerical methods for when you couldn't find an antiderivative or something like that. So what we're going to talk about now are improper integrals. Okay, wait, that's not what I wanted. The hell, there we go. So I guess we should contrast the improper integral first with a definite integral, like what I was saying. So a definite integral is when you have an integral from a to b, f of x dx, and very importantly, f of x is continuous on your interval ab. So you have no asymptotes or stuff like that. So a definite integral you can compute, remember, it's defined to be the limit as n goes to infinity of the sigma I equals 1 to n of f of xi delta x. But, most of the time, how do you actually do this in practice? You do f of b minus f of a. Because you're basically assured to have an antiderivative if you're continuous. But the question is, what if you're not continuous? Okay. What if f of x is not continuous, or the interval on which you want to evaluate is not finite? Okay, that's what makes an improper integral. So these cases are going to be improper integrals. Okay, you have some sort of discontinuity on your interval, or your interval is infinitely long, basically. Okay. So I'm going to show you how to do this, basically. So let's do our first example of an improper integral. So an improper integral would be something like, let's integrate from 1 to infinity 1 over x dx. Okay. Now, do you have an antiderivative for this function? Yeah, exactly. So the fundamental theorem of calculus would basically tell you, if you want to calculate this thing, you would do f of the top minus f of the bottom. But then it's does it make sense that infinity is not actually a number? You can't plug it into natural logarithm. It makes no sense to say, hey, take the natural logarithm of infinity minus the natural logarithm of 1. You just don't know what to do with that. Okay, because infinity itself is not a definite value. That's why you call them definite integrals. There are particular finite values in which you are plugging in. So, what do you do with this? Well, there's actually a pretty easy way to deal with it. Let's talk about it. So if you think about what's going on here, you have your function 1 over x, which looks something like this. Okay, now the region over which we are integrating goes from x equals 1 all the way off to infinity, right? So that's like all of this. And it keeps going forever and ever and ever. So that's like the issue here. So imagine, normally we're supposed to go from x equals something to x equals something else. So let's say instead that we were going from 1 to b. So now I'm going to integrate from 1 to b. Would this have an answer? Or would you be able to calculate this value if I was integrating from 1 to b, is my question. Yes, and it would be equal to the natural log of b minus the natural log of 1. Do we all agree with that? Which actually is just going to be, because what's the natural log of 1? What's the natural log of 1? 0, right? So you just get the natural log of b. Okay, now, I don't want to integrate from 1 to b. What do I actually want to integrate to? Like, the real problem that I want to deal with. 1 to infinity. And this is where you get the idea of, like, how about this? Why don't I let the limit of b go to infinity for this integral? Oops. That should be the same as just doing the integral from 1 to infinity. Does that sort of make sense to everyone? Like, if you want to do the integral from 1 to infinity, that should be the same thing as doing the integral from 1 to b, and then taking the limit as b goes to infinity. And this is what ends up working for me. So now what I can do is I can do the limit as b goes to infinity of the natural log of b. And I should be able to get my answer. Now here's the problem. If you take the limit as b goes to infinity of the natural log of b, do you get an actual answer? Like, does that approach some particular value? What happens to this limit? Like, if you want to take the limit as b goes to infinity of the natural log of b, do you get a value for that limit? It is undefined, so the limit, what? What do we call it when you get an undefined value like that for the limit? It does not exist yet. Okay, so you get two cases. If the limit of the definite integral does not exist, then the original improper integral is said to not converge. But if the limit of the definite integral does exist, then the original improper integral is said to converge. So what happened for trying to take this, the improper integral of 1 over x did not converge or diverged. You cannot calculate that area. It's an infinite area, basically. If you were to keep on accumulating the area under the curve 1 over x from 1 to infinity, it just keeps on getting bigger and bigger and bigger and bigger, and it doesn't head to some particular value. Do we get what I mean by that? Like, if you start accumulating all this area from 1 all the way off to infinity under that curve, it just keeps on growing. It doesn't converge to anything. Okay? But if it did go to some particular value, then we would say that it does converge.